Hello everyone, I hope all of you doing fine, and we have just started our journey. We have started our discussion in our journey to crack most important exams, most important physics entrance exams, right? So in our last discussions we have discussed most important topics in quantum mechanics, and I am just continuing from there. Okay, so please share this video and don't forget to watch earlier recordings if you have not watched them. They are going to be very beneficial for all of you. Okay, share with your friends and don't forget to subscribe and give a like if you get benefit from this. Okay, I hope if you have any comments and some suggestions, if you can provide in comment section. Okay, let's start it. So I am just continuing from the last video. In today's lecture I am going to first discuss about commutator bracket. So what is commutator bracket? Commutator bracket is provides a very important framework in understanding of quantum mechanics in mathematically. Okay, there are two operators, a cap and b cap, right? Commutator means ab minus ba, anti-commutator means ab plus ba. So if they commute, a and b if commute, then what happens? Then they have simultaneous eigenvalues. Means if, for example, if position operator x and momentum operator p commute, let, for example, they don't commute. We know that position and momentum operator commutation have I squared value, right? They don't commute. Commute means they have 0. This commutator bracket value have 0. Commute means, okay, if they commute, then their uncertainty product delta x dot delta p becomes 0. So what that means is that if we measure position extremely precisely, okay, then we can also measure momentum, but we know that is not possible. According to quantum mechanics, we can't measure both of them simultaneously. If we measure position precisely, then momentum becomes infinite, right? This is very important in quantum mechanics. So first rule in commutator bracket, this is the linearity as anti-symmetry property. This is the first is anti-symmetry property. AB computation of AB is equal to minus computation of BA. And second is the linearity property. They distributed like this. This is linearly distributed. Okay, this is Hermitian conjugate. Hermitian conjugate of AB. Then the dagger is gone inside the bracket. Okay, and distributed on them. And B comes earlier and then A. Okay. Then fourth property is if A commutation of A into BC, commutation of A with BC is first take AB, C goes outside, and then plus B comes outside, then commutation of AC. Okay, this is the fourth property. And fifth property is, this is the distributive property. Okay, AB, A commute with commutation of BC plus B commute with, this is the Jacobi identity, right? It's very important. This is the Jacobi identity. Okay, and fourth, if A commutes with an A commutation bracket of A and a function of A, then commutation bracket becomes 0. Okay, but look at here, if commutation bracket of A with a function of B is another quantity, right? Okay, then first of all you need to differentiate the function of B, then computation of AB, right? Then eighth property, function of A and function of Z, they will commute, commutation becomes 0. And ninth property is function of A and function of Z becomes 0. That is same if and only if AB commute. This property only can be satisfied if A and B commute. Okay, and ninth property is a and b to the power n, then m's there is you need to differentiate b first, okay, differentiate it, okay, and b to the power n minus 1 and commutation of ab, okay. And 11th property, a to the power n and b, and they differentiated a to the power n first, then commutation of ab, okay. And then 10th property is if small b here is a scalar quantity, therefore commutation of a and scalar quantity becomes 0, okay. That's very important. So we have moved to position and momentum operator commutators. Look at here, position and momentum operators. If we take position operator as k1 and pj is momentum operator, their commutator is I squared delta ij. This is the delta function. Delta function have some property. If ij have same value, then value is 1. If ij become different, then value becomes 0, okay. Q here qi should be qi. If qi is x, then p should be x component of the momentum, okay. Look at here, the value is I squared. If we we reverse that, this is the anti-symmetry property, minus I squared, okay. We can write position operator in momentum space. There is position space and another is momentum space. Remember that in momentum space, position operator can be written as like this, as this I squared equal I squared into del p suffix j, okay. This is the important property. Then Hilbert space. Hilbert space is the space in which we put all of the wave functions. Wave functions belongs to a system. All of those possible wave functions can be put in a space, like we put a football in a space, or I am in a space, you are in a space, okay. We are in a three-dimensional space and there is a 4-dimensional time. Like this, Hilbert space is infinite dimensional, means there can be infinite dimension. Space in which set of functions, these are the wave functions, goes to infinity from orthonormal basis. Orthonormal basis or normal, the wave functions are normalized and orthogonal, okay, both at the same time, orthogonal and normalized. This space is infinite dimensional, right? So orthogonality condition of wave function. Orthogonality, if there are two wave functions psi m and psi n, if m not equal to n, then their probability or product becomes 0. This is the, we can write in matrix form, okay. We can toss it with delta function. If m equal to m equal to n, then it becomes 1, and if m not equal to n, then this becomes 0. Uncertainty relation between two operators. Look at this, delta a, uncertainty product. We can calculate uncertainty product from this formula, and delta b is uncertainty product. If this is multiplied, both of them, uncertainty product will becomes greater than equal to half of modulus of expectation value of commutators. So we have discussed earlier, if x and p commute, this becomes 0, then this also becomes 0. Uncertainty products become 0. That means we can measure them simultaneously, okay. Let's move on. Expectation value, we will encounter most of the times expectation values in our exams. This is very important. Expectation value we can calculate like from this formula. We can integrate from the limit which the system have. In this case, from minus infinity to plus infinity. If a one-dimensional box is given and box goes from 0 to L, then we need to put the limit from 0 to L. Okay, here minus infinity to plus infinity is the limit, then psi star, this is the operator for which we need to calculate expectation in that system. Okay, and psi is wave function, star is the complex conjugate. Okay, then divide it by the probability. Okay, minus infinity to infinity psi star psi dx, the scalar product it's called. So that is, we can write like this in bracket notation. This is the bra and this is the cat, bra and cat, bracket. Okay, bracket notation. So this is the expectation value, and expectation value is also equal to average value of that operator. Look at this, A is operated to a wave function, then eigenfunction, then this is the eigenfunction psi, then this is the eigenvalue, lambda is the eigenvalue. If we operate operator in a wave function, eigenvalue comes, then wave function is regenerated. Okay, this is the basic definition, most important in our quantum mechanics. Okay, then we can also operate bra in bra psi here, and we will get like this. And if lambda, we can calculate this is the eigenvalue or average value. So from this definition we can understand that average value is also equal to expectation value. Okay, look at this. So if the state of the particle is in an eigenfunction of the operator a cap, then expectation value of a cap will be equal to the eigenvalue or average value. Okay, so expectation value of A, we can, this is also very important, we can also calculate from here. If the wave functions of the system are put in superposition state, then this is the constant or the normalization constant of attached with every possible wave function in that superposition. Okay, then take its square, the square of that normalization constant, and multiply with eigenvalue, then divide it with modulus of c square. We can calculate also from this. Okay, there cn square, modulus of cn square is the normalization, it's become equal to 1. Okay, normalization constant, if you square it becomes 1. It means it's 100% probability of finding that particle. Okay, let's move on. Tricks. Okay, tricks discussed. Let's discuss tricks here, some important tricks. If wave function is a is e to the power I kx minus omega t imaginary, then the expectation of momentum operator becomes h cut k, and expectation of momentum operator square means p square, expectation of p square is equal to h cut k square. Okay, and if wave functions are real, like a sin kx minus omega t, no imaginary term here, real, purely real, then expectation value of momentum becomes 0. P square, we need to calculate it, it's not 0. Remember that this expectation of p square is not 0. Okay, we need to calculate here. K is the p square by twice m, or kinetic energy, we can also compare it with this. Okay, this J is the probability current density. Probability current density is h cut by twice im into psi star delta psi minus psi delta psi star. Okay, and we can write like this: J is equal to expectation value of p divided by m. If, look at this, if J is equal to 0, if probability current density is equal to 0, then expectation of momentum is 0. It's important tick. Most of the cases, if the operator is odd, then, and if also the wave function is symmetric about x equal to 0, like this, yes, it is symmetric about x equal to 0, right, in this case, then expectation of the operator A If it is odd operator, then it becomes 0. Expectation of A becomes 0. Okay, and the important thing, if potential is symmetric, look at this. If I put here a minus sign inside it, it becomes positive, means it's symmetric. If potential is symmetric, then wave function is symmetric and anti-symmetric both, right? Wave function becomes symmetric and anti-symmetric. Some important integrals, this is very important. These are the integrals we use most of the time to calculate expectation values and some calculations in quantum mechanics. So this is the beta mn is equal to 0 to 1 x to the power m minus 1 minus x to the power n minus 1. It's very important integral. Then beta mn is equal to gamma m gamma n divided by, this is the property of beta function, twice gamma m plus n. This is the property of gamma function, gamma m is equal to integration of 0 to infinite, limit, remember that limit, okay, 0 to infinite, not in minus infinite to infinite. Most of the time students makes wrong in exams. And x to the power m minus 1 e to the power minus x dx. And property of gamma function, gamma n plus 1 is equal to n gamma n. Okay, very important. But gamma n is not, in case of integer, that is not happens. Okay, in case of integer like 1 to 3, this is the case for only half integers, like half, 3 by 2 half integers, gamma n plus 1 equal to n gamma n. But if this is for in case of the integer values, gamma n is equal to n. Okay, gamma n is equal to n, like this, gamma 1 is equal to 1. Okay, this is the important integral, minus infinity to infinite, x to the power minus beta x square dx equal to 0. Here x is odd, for odd function this integral becomes 0. There x to the power n, if this is not odd, then this is the value gamma n plus 1 by 2 divided by 2 beta to the power n plus 1 by 2. Okay, remember these two important formulas. Okay, so Schrödinger wave equation. Schrödinger wave equation, there are two types, time independent and there is time dependent. Okay, time independent is minus s square by 2m d square x by dx square psi x plus p x psi x equal to e psi. Okay, time dependent is minus s square by twice m. This is the Hamiltonian of that. Okay, this is the Hamiltonian. Okay, kinetic energy plus potential energy, right? D square by dx square psi xt, here dependent on x, so time is coming here, plus px psi x comma t equal to I x cut dt of psi x t. This is the time dependent energy operator. This is the energy operator. Okay, when it depends on time. So look at very important line, it is an eigenvalue equation. Okay, if it doesn't depend on time. This Schrödinger wave equation is an eigenvalue equation, that means wave function is regenerated if and only if it is independent of time. It's not an eigenvalue equation. Okay, if it depends on time, then Schrödinger equation is not an eigenvalue equation. Okay, Schrödinger cat experiment. Schrödinger imagine a very interesting experiment in which his cat, he have a cat, he put his cat in a box and put some poison in that box like this, and he experiment, this is a thought experiment actually. He imagined that what would be the result if the measurement is done. There are two possibilities, cat is alive and cat is dead. So in this case, cat is in superposition of state between dead and alive. Superposition of state, this is the very important understanding in quantum mechanics. Superposition and entanglement, decoherence, coherence, right? Psi is the wave function, is superposition like this. This is the normalization constant, this is the normalization constant for psi 2, this is the normalization constant for psi 3. So here wave function is superposition of dead and alive. Look at this wave function. A cat is standing, so it is alive, and here cat is dead. Okay, here normalization constant is 1 by root 2, means if you square c1, then you will get half. If you square this, you will get half. 50-50 chance that 50% chance that cat is alive, and 50% chance that cat is dead. So wave packet by superposition, wave packets, right? These are the wave packets. There are so many plane waves, infinite number of plane waves. When combined together in superposition, we get a wave packet, right? If we done the measurement, if we do measurement in this wave packet, we will get only one result out of many infinite plane waves combined. Okay, this is the wave function is collapsed to a single possibility. There are so many possibilities that can result can be different. Okay, if we done the measurement here, then wavelength of that plane wave becomes lambda 1. If we done that measurement sometimes later, we will get a different value of that measurement, a different result. The wavelength will be lambda 2, right? Because there are so many possibilities in combined in that wave function. Okay, momentum, this is the eigenvalue equation. P cap psi is equal to p psi. P is the eigenvalue. So let's move on. Probability current density. Delta dot j is equal to ddt of rho is equal to 0, right? Delta dot j is the divergence of that quantity, current, divergence of current is equal to minus of, if we put that value in other side of the equal sign, okay, it becomes minus of ddt of rho, means divergence of here, its probability flows, like, right? Divergence of here, current is diverging from this point to this point. Okay, then the density of that function will be decreasing, therefore it is minus. Okay, density is decreasing, means probability is flowing from one point to another point. This is called probability current density. Current, like it's flowing. Okay, this is the formula. J is equal to h by twice I am psi star delta psi minus psi delta psi star. Okay, then wave function in position and momentum space. So wave function we can write in momentum space also. In momentum space is equal to 1 by 2 to 4 twice by h cut integration of minus infinite to infinite psi x e to the power minus I px h cut dx. And in position space we know we use most of the time, right? Psi x is equal to 1 by root pi h cut integration of minus infinity to infinity psi p e to the power I px by h cut dx. If you remember one formula, one space representation, you can write both of them, right? It's very easy. So thank you for joining me in this today's lecture, today's episode, and looking forward to see you on the next episode. So thank you for watching, and keep sharing and keep learning, and this is going to be very, very helpful. So thank you.